Today, I'd like to discuss the idea of de Broglie wavelength. In 1924, Louis de Broglie proposed the idea that matter, like light, has a wave-particle duality. Basically, this means that sometimes we observe that matter acts like a wave, and other times it acts like a particle. This idea plays into the field of quantum mechanics, which studies really small things rather than everyday objects. But how do we know that this happens if we can't see it happen in our everyday lives? Well, we have to look at Young's double-slit experiment to really see what happens. In this experiment, an electron gun shoots electrons, extremely small electrically charged particles, on a path colliding into a wall with two small slits and a piece of electron detecting paper behind it. Thousands of electrons were fired through the slits, and while expecting a normal two-line pattern, instead they observed an interference pattern. Rather than the two slits projected onto the sheet, the pattern suggested that the electron particles acted as a wave. But what is an interference pattern, and what does it tell us about the properties of the electron? Well, imagine doing the same experiment, but this time with water and a wave machine. As the water heads toward the wall, it is in one single wave. However, once it reaches the wall, it moves through the two small slits and creates two smaller waves. These waves then interact with each other. The low and high points effectively cancel each other out. Don't believe me? Here's Dr. Mikichi, professor of chemistry at Saddleback College, to explain what's going on.
That's right. Even though we're used to matter acting like a particle, it can and does act like a wave. All right, I've got more important things to do.
Thanks, Professor. Now, to better understand what's going on, let's go to a situation you might be more familiar with. When our soccer player kicks the soccer ball towards the net, you expect only one ball to hit the net in one place, and that's exactly what you see. So why does the soccer ball act differently than an electron? After all, isn't the same basic thing occurring? Remember, quantum mechanics studies how really small particles act, whereas classical mechanics studies everyday objects. So when figuring out why the soccer ball acts differently than the electron, we must look at it through the lens of the scientific method. The soccer ball and electron, while having different masses, look to be nearly identical. So we can reasonably guess that these two things act differently is directly correlated to their mass. In other words, we can assume that really small things like electrons, protons, and some molecules have the ability to act like waves, while really big things, like soccer balls, can't. How much mass an object has determines its properties as either a particle or a wave. It's that simple. And according to de Broglie's equation, that's exactly what we see. But let's pretend the soccer ball does act like an electron, just to illustrate what's actually happening. So why doesn't the soccer ball act like this? Well, back to de Broglie's equation. The wavelength of any object with its mass is equal to Planck's constant divided by the object's mass times its velocity. For the soccer ball to act like this, its mass would be so small compared to its volume, it practically wouldn't exist. And that's why we see this behavior in really small things, because they have practically no momentum, meaning that they can have a measurable de Broglie wavelength. Why does this matter to us? In our day-to-day lives, it really doesn't. But we only know that this phenomenon does happen, not why it happens. So stay curious and never stop discovering.